So this is the Bellman equation that we were just talking about, right? So the value of a state is the max over all the actions, the reward that you get for taking that action from the state, plus the discounted value of the state you end up in, weighted by the probability that you end up there. So this should look familiar, right?
No, it doesn't look familiar at all. I mean, there's a V, there's a max on the outside. There are more parentheses. It's a reward of SA instead of what? You're making this up.
Well, okay. So first of all, parentheses shouldn't be an issue, right? Parentheses just let you group things. But yeah, I think you did actually explain this a different way in the other lecture. So I use V for value instead of U for utility.
Okay.
And I think of rewards as being issued as a function of taking a state in an action. So, sorry, taking an action in a state. Which is to say that you're in some state of the MDP. So in particular, if we're in some state S and we take some action A, we get some reward for having done that, RSA. And then we land in some new state S prime. I guess that is different than how you were talking about it before.
Yeah, but when we went over the definition of an MDP, I did point out that you could think of reward as a function of state, or as a function of state in action, or as a function of state action in next state, and they were kind of all mathematically equivalent. So this is what we're going to be doing for the rest of this class. We're going to be talking about it this way.
Yeah, I'm used to thinking about V as being the value function. So I think I'm going to slip into it no matter what. We might as well just switch to it.
Okay, so we're going to do V's, and we're going to do R, S of A's, but everything that we learned before in our Scooby-Doo flashback still holds now.
Yeah. It's just it's notational difference, and otherwise it really leads you to the same stuff.
Okay, we shall see.
So what the Bellman equation is supposed to represent is the sequence of rewards received by an agent that's hopping around in the world. It starts off in state S1, it takes action A1, it gets reward R S1 A1 for that. Then it lands in state S2, and from there it takes action A2 and receives reward R S2 A2 and ends up in S3, and this whole process just continues ad infinitum.
Okay, so you're seeing a bunch of SAR, 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 SARs.
Exactly, right. You can think of history as just being SAR, 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 SAR.
Oh, so it's like a pirate with a reverse lisp.
Yeah, I guess that's one way to think about it. So when we talk about the value of this sequence, it's almost as if what we're talking about is the value given that we start off in some state S.
Mm-hmm.
And we notice that eventually that we're going to get to some new state S, and that value can also be represented by this value function. And so that's what gives us this recursive form, that the value of the next state can be plugged in to represent the infinite rest of the sequence.
Sure, that's sort of the whole point. Okay, how about that?
Cool. All right, so we're going to now try to mess this up a little bit by thinking about infinity a slightly different way.
As bigger or smaller?
Just starting it in a different place.
Okay.